Dear students, welcome to my class on galvanic cells, the third session. In this session, we will be dealing with single electrode potentials and also standard electrode potentials. So, first we have to see, that is, we have been saying that electrode potentials for all the classes, but we do not know how the electrode potential has been originated. So, now let us see how it originates. Now, origin of electrode potential is like you put a metal in its own ion solution. So, this is the metal in the solid form, which is inserted in its own ions. I am putting it as aqueous to show that the solution is of metal ions, okay, and not in the solid form. Now, what happens here? There are two possibilities, that is, you know that a metallic substance, anything metallic, has got metal ions placed at their lattice points, and you have the valence electrons as a sea of electrons around it. Now, during that condition, there are chances like this metal ion can come out of the metal, and also there are chances that the ions present within the solution can get into the metal lattice. So, there are two tendencies. First tendency, I can represent it as the metal which is in the solid form existing in the metal rod, it goes into solution as metal ions with keeping their electrons on the metal rod. Okay. So, here the metal loses its electron, it remains on the metallic part and it goes into solution as Mn plus, where N is the valency of the metal ion. This is one tendency. At the same time, the ions present in the solution, they may take up electrons to form the solid metal and they enter the crystal lattice, or you can say that it deposits on the metal part. Here you can see two reactions I have written. In the first case, it is a metal getting oxidized to form its metal ion, and in the second case you can see the metal is getting reduced forming metal. Here see the metal getting oxidized to form. So, I will put this reaction as oxidation and this reaction as reduction, where the metal ion gets converted into metal. Now, let us consider the case here. Here the metal is going into solution as Mn plus, and Mn plus ions they get deposited on the metal. So, there are chances for two reactions to take place, and finally what happens is there will be some metal ions which has been originated from the metal into the solution and some metal ions which are deposited. Now, when we consider these two separately, in the first case the metal is getting converted into metal ions, there will be accumulation of electrons, electron accumulation. When electron accumulates, you know that the electrode becomes negatively charged. So, this is not connected with the anode or cathode. You can say there will be accumulation of electrons and therefore, the polarity of the electrode will be negative. So, this will be with a negative polarity. Okay. But according to our convention, here oxidation is taking place and therefore, this is the condition when an electrode is an anode. Here you can see the metal ion from the solution is getting reduced, that means it takes up electron and then gets converted into metal. So, what will happen? If such a reaction is taking place at an electrode, the electrode becomes electron deficient, or you can say it will have a positive polarity. it will have a positive polarity. And we know that this is the electrode at which reduction takes place, and that is actually we will have to consider that as a cathode. That is what I told, there is no relation between anode or cathode with the polarity of the electrode. So, this is what is happening here. Now, what happens is I am going to take the first condition in which here the metal is getting oxidized. So, here oxidation is occurring and there will be electron accumulation on the metal part. At the same time, in the solution you will have the Mn plus ions accumulating here, Mn plus ions in solution. Now, what will happen? The metal part has got a negative charge and the solution part is having positive ions. Naturally, there will be an attraction, and what happens is there will be a crowding of positive ions over here and an interface will be developed between the metal electrode and the solution. So, you can say there is an electrical double layer, because the electrode part or the metal part which contains the negatively charged and positive ions crowding near it. So, the electrical double layer developed will produce a potential. Potential is developed and this potential is known as electrode potential. In the other case, this will be in the opposite way, that is, instead of electrons accumulating on the metal part, when reduction occurs there will be a deficiency of electrons, automatically the negatively charged ions get accumulated, there will be an electrical double layer formed and a potential developed, and that will be the electrode potential of that particular electrode. So, in both ways, it can be either oxidation or reduction, there will be an electrical double layer formed due to accumulation of charges, and that is responsible for the electrode potential. Okay. So, now let us see what do you mean by a single electrode potential. Single electrode potential means it is a tendency of an electrode to either gain electrons or lose electrons when it is in contact with its own ions, and the equilibrium potential developed due to the separation of charges is known as the electrode potential. Now, the factors influencing electrode potential, they are metal and its ion. So, from metal to its ion, if I take zinc, it will be a different potential. When I take copper, it will be giving another potential. So, it depends on metal and its ion. Now, if you fix the metal and its ion again, it depends upon the concentration of the metal ion in the solution. So, if I am taking copper metal in contact with 1 molar solution of copper 2 plus ions, the concentration is 1 molar. So, what happens here is you will have a certain potential. Okay. Now, again I am taking copper metal in contact with a solution of 0.1 molar copper ion solutions. Here the potential will be different, because you are taking copper and copper ion, but the concentration of the electrolyte which I have taken is different, and therefore, it depends upon the metal ion concentration. It depends upon nature of the metal and ion, on its concentration of its ionic solution taken, and also one more factor, that is temperature. So, these are the 3 factors on which the electrode potential depends. Now, how will you express electrode potential? Now, we have seen 2 cases where the electrode is undergoing oxidation and electrode is undergoing reduction. So, you can say when an electrode is undergoing oxidation, automatically we can say there is an oxidation potential. When electrode is undergoing reduction, we can say it is a reduction potential. So, you can say it in both ways, either the oxidation potential or it can be reduction potential. here the difficulty is when I say, if I am representing the potentials of electrodes as oxidation potential, another person might be representing in the form of reduction potentials. So, there will be always a difference between these two. So, what IUPAC has done is, IUPAC is fixed a rule to represent electrode potential. So, what they have done is that electrode potentials should refer only to reduction potentials, should represent it as reduction potentials, and that is the reason when I take a single electrode, I represent the electrode reaction to be reduction. So, that is a IUPAC rule to be followed. Okay. Next, we will be seeing standard hydrogen electrode. Standard hydrogen electrode, and actually for convenience we represent it as SHE, that is standard hydrogen electrode, or you can also put it as NHE, where N stands for the word normal, that is all. Instead of standard, we will be saying as normal hydrogen electrode, both are same. So, this is an arrangement of a picture showing how a standard hydrogen electrode or normal hydrogen electrode is set up. Now, why do we need this? The need for standard hydrogen electrode is because you cannot take the single electrode potentials as such, you cannot measure it with a single electrode. If you have to have a flow of current and measure the potential, you need 2 electrodes. So, to fix a standard for that, we are introducing an electrode known as standard hydrogen electrode, and that is how we are going to learn about standard hydrogen electrode. The standard hydrogen electrode, as you can see, it contains a glass tube which has got a wider end at the bottom. You have a wire usually sealed in a glass tube, and at the bottom you can see it is filled with mercury to make a very good electrical conductance, and from that you have a platinum foil which is coated with platinum black, coated with platinum foil, coated with platinum black, and from here you take the connection to the external circuit. You have a side tube over here through which you can bubble hydrogen gas, and hydrogen gas for standard hydrogen electrode has to be bubbled at 1 atmosphere pressure, or to be more accurate you have to say the pressure to be 1 bar. Okay. Now, you have to take some solution which contains H plus ions, that is I am going to take 1 molar HCl solution, and it is very important the concentration has to be 1 molar, only then it becomes a standard hydrogen electrode, because we are fixing the standards and we fix it, and we are going to fix the potential for standard hydrogen electrode. Here the gas is bubbled through this, it comes into contact with H plus ions, where you can set up the electrode as you will have a platinum wire and then hydrogen gas. It is very important, the pressure has to be 1 bar or approximately 1 atmosphere in a solution of H plus, where the concentration is 1 molar. So, this is how we can represent a standard hydrogen electrode. So, this is for measuring single electrode potentials. Now, how will you measure the single electrode potential? Whichever the electrode you require to measure the single electrode potential, you just take the electrode, couple it with the standard hydrogen electrode, connect it, measure the potential, you will get the potential of the cell of the electrode of which we have to measure the electrode potential and the standard hydrogen electrode. So, connecting that I will be getting a potential. If you know the standard hydrogen electrode potential, you can get the potential of the electrode. So, that is how we are going to measure the single electrode potential. Now, when connected, there are 2 conditions. We were just mentioning that you are going to connect the given electrode with a standard hydrogen electrode. When we connect a standard hydrogen electrode, there are 2 options that may occur. One is the electrode may undergo reduction. Similarly, there is a second choice is the electrode may undergo oxidation. So, there are two cases. Now, if the electrode connected with standard hydrogen electrode undergoes reduction, I will have to put SHE on the right hand side, because SHE will be the anode which undergoes oxidation, and our electrode which undergoes reduction is kept on the right hand side, because that is having reduction. If it is so, the electrode potential is given a positive sign. Now, when the electrode connected to SHE undergoes oxidation, again we have to put the electrode on the left hand side and SHE on the right hand side. So, here the electrode undergoes oxidation when connected to SHE, and in this case the electrode potential is given a negative sign. So, when reduction occurs, we give a positive reduction potential, and when oxidation occurs, we give a negative reduction potential. That is all. Now, how it is measured? Before that, let us see what do you mean by a standard electrode potential. An electrode is called to be a standard electrode if the electrolytic solutions involved in the electrode should be of concentration of 1 molar, or you can say it as 1 mole per liter. So, the concentration has to be 1 molar. Now, if there are gases involved, it has to be at a pressure of 1 bar. Pressure has to be 1 bar. And next factor which we have to keep in mind is that the temperature has to be 298 Kelvin. So, these factors has to be maintained, and if we maintain all these, the electrode is said to be a standard electrode, and we use a notation. If I am maintaining the standard conditions for a particular electrode, I represent that as E naught. So, what does it show? This electrode is under standard conditions of solutions in 1 molar, gases at 1 bar pressure, and temperature at 298 Kelvin. Now, the standard cell, we are going to combine it with the standard electrode, that is SHE. Now, when I combine these two, told you, you will be getting a cell. Now, from that what we do is, we take E naught of cell. That is what we are going to measure, because we are connecting these two electrodes with together and measuring the potential of the cell, and by equation E naught of a cell is equal to E naught of cathode minus E naught of anode. Okay. So, in the case if the electrode acting as reduction, that will be the cathode, SH will be the anode, and when we take the EMF of the cell, you can minus the value of SHE and you will get the potential of the cathode. Now, what we are going to do here is just say we are going to set up a standard, okay, and that was SHE. And for arbitrary sake, we say that the potential of SHE is equal to 0 volts. It is not exactly 0 volt, but we consider the potential developed on a hydrogen electrode is 0. We are considering it is just for setting up a scale, and based on that, in reference to standard hydrogen electrode, how much potential you are getting for any other electrode is taken as the standard electrode potential of that particular electrode. So, that is how we find out the standard electrode potentials of any of the electrode you require, and we make a table of all these standard electrode potentials known as electrode potentials. Standard electrode potentials, we call it as electrochemical series. See, here is how these are all in reference to hydrogen, standard hydrogen electrode. And you can see here, this is at the center, you have the hydrogen electrode placed, whose potential is taken to be 0. Okay. And above hydrogen, you have lots of other electrodes whose standard electrode potentials have been determined. And these values are arranged in such a way that the electrode potentials, the reduction electrode potentials are increasing as we come down. See, it is keeping on increasing and reaches the highest value for the last one, which is shown in the red color. Okay. And about the elements, when you consider, fluorine has got the highest reduction potential. And you can say that the least reduction potential is given by lithium, which is written on the top. It is again given in red to show that it has got the highest value. Okay. Now, as we come down, you can see the reduction potentials are increasing, or you can say that an element lying below has got more tendency to get reduced rather than an element lying above it. So, you can take any of the element, any pair, and you can say when these two are combined, which will oxidize and the other one will be reduced. Here, suppose for example, I am going to combine two, like let it be magnesium and aluminum. Magnesium and aluminum. I am going to combine these two electrodes. Here you can see the value of magnesium is minus 2.363 and that for aluminum is minus 1.662. Okay. So, from this value I can understand that this is minus 2.363 means its reduction potential is negative, means it prefers more oxidation. While in the case of aluminum it is minus 1.662, which has got a lower value, which shows that it prefers more of reduction rather than oxidation. So, when I combine these two, I am sure magnesium will undergo oxidation. So, magnesium can act as an anode, while aluminum, which has got a lower oxidation tendency or higher reduction potential, that will be cathode. Okay, like that you can take any pair. So, that which is lying above will get oxidized, the other one will be reduced, because as we come down the tendency to get reduced is greater. And one more point, if a substance like to get reduced, it takes up electrons and they can act as an oxidizing agent, because they will be taking electrons. Those which has got tendency to get oxidized, they do not like electrons, they give their electrons out, and what happens is they reduce the other elements. So, which has got a tendency to get itself oxidized will be a reducing agent, and those which likes to get reduced will act as an oxidizing agent. So, that is about electrochemical series. Now, let us see what are the applications of electrochemical series. Electrochemical series helps to predict the relative ease of oxidation of various elements, whether they will get oxidized or reduced. I told you any element lying above, okay, or I can say it in another way, like you can have any element with the lower reduction potential, lower reduction potential. We know that reduction potentials are increasing as we come down. Okay. So, lower reduction potential will be those lying above. So, any metal with lower reduction potential shows a tendency to get oxidized. They get oxidized rather than reduced. Which has got higher reduction potential, their reduction potentials are high, that is those lying towards the lower part, they usually get reduced. Okay, that is what we understand from this part. Next is electrochemical series tells us about a constitution of any cell combining any two standard electrodes. You can take any of the standard two electrodes and you can say which electrode undergoes oxidation and which one undergoes reduction just by looking at their standard values. Okay. So, you can say how can you construct a cell, which will be the anode and which will be the cathode. For example, again let us go back. I am going to take copper and I will do it with lead, copper and lead. So, there are two values. See, in the case of lead, Pb, Pb2 plus, the value is minus 0.126 volts. Next one was copper, copper 2 plus, the electrode will give you a standard electrode potential of 0.337. By the way, the sign is very important. In the case of lead, it is minus 0.126 and in case of copper, it is plus 0.337. What does it show? Lead has got lower reduction potential and that is why it has got a negative sign. This is lower reduction potential. This has got very high reduction potential in comparison to lead, and therefore, when I construct a cell taking lead and copper, what happens is lead will always prefer oxidation. So, lead will be the anode and copper will be the cathode. So, you can take any of these two like this and you can construct a cell and you can say which will be the anode and which will be the cathode, and you can give the electrode reaction as well as the cell reaction too. Okay. So, that is the second application. Third one is the electrochemical series helps us predict the direction of displacement reaction. If you remember, we started with a displacement reaction in which we put zinc in copper sulphate solution. The reaction was zinc plus copper sulphate aqueous giving zinc sulphate aqueous plus copper solid. Here the zinc displaces copper, forming zinc sulphate, and the copper is precipitated out. Now, how will you explain this with respect to the electrochemical series? We are taking two, zinc and copper. Copper we have already seen, just now I have marked it, that is copper with a potential of 0. It is written here. Now, what about zinc? Zinc has got a value of minus 0.7627 volts. You can see here the value of zinc is always negative, which shows that it is very lower in reduction potential value. So, zinc prefers oxidation rather than copper. So, what happens is copper, which is in the oxidized state in copper sulphate, it is being replaced by zinc and zinc occupies that position. Okay. Next is the electrochemical series tells us how to constitute a cell, set up a cell by combining two things, two electrodes. It gives us the direction in which the displacement takes place, and finally, it helps us to predict whether a metal can displace hydrogen from its dilute solutions or not. Displace hydrogen from dilute solution in the sense, if I add metal to an acid solution, whether we will be getting hydrogen gas or not. For example, if I put zinc in dilute HCl, you get zinc chloride plus hydrogen gas evolved. Now, why do the zinc give hydrogen, or you can say that zinc is displacing hydrogen from HCl? You just check with the electrochemical series. Hydrogen has got 0 reduction potential, while the value of zinc is, as we have seen, that is equal to 0.7627 volts. So, we know that zinc is more electropositive, it likes to get oxidized. So, what happens is it displaces hydrogen. So, any metal lying above hydrogen has got a higher oxidation tendency than hydrogen, and therefore, they will displace hydrogen from dilute acid solution. Okay. But in the case of copper, you can see it is below hydrogen. You put copper, you will not get hydrogen evolved from dilute solution. You take in silver, you add to acid solution, you will not get hydrogen atom, because they lie below hydrogen in the electrochemical series. Next, we will see a problem in which you have E naught of chromium given, that is given E naught of chromium is equal to minus 0.74 volts, and that of tin is equal to plus 0.15 volts, and we are asked to calculate the potential of the standard cell, which is obtained by combining these two. So, we have got two values. We know that E naught of cell is equal to E naught of cathode minus E naught of anode. So, here we have to identify which will be the cathode and which will be the anode. Cathode is which it is undergoing reduction. Here we know when we compare these two, that of zinc and tin, chromium and tin, tin has got higher reduction potential, and therefore, tin will undergo reduction. So, this will undergo reduction and this becomes the cathode, and obviously, chromium, which has got a lower reduction potential, will undergo oxidation, and that will be the anode. So, you can calculate it, that is cathode is 0.15 volts minus of 0.74 volts, and when we do it, we will get the answer as 0.89 volts. So, first the thing is you have to identify whether which is the cathode and the anode from the values given, and only then you can apply that to the equation, otherwise the answer will go wrong. So, today we have been seeing in this session like what do you mean by a single electrode potential, how a single electrode potential can be measured, and what do you mean by a standard electrode potential. You have to maintain the standard conditions, and by measuring the standard electrode potentials relative to standard hydrogen electrode, you get a series known as electrochemical series, and which has got very high applications in electrochemistry. And that is all for today. Thank you.